Okay, excellent. So PIRE, MotU, FORCE, a whole bunch of acronyms. What's it about? What I would like to convince you is that all of these efforts form a large, happy family of collaborative research, which basically we are very much enjoying. So let me start then with the next slide. I think you need to advance it, or can I? I think you need to. Oops. Okay, good. So first of all, in PIRE, I think most of you know that our work is on the thermodynamic studies of the stability of polymer-derived ceramics, fibers, metal organic frameworks, nanocarbons, and related materials. We've been collaborating, of course, with Gurpreet, also with the Darmstadt group, Gabriela and Ralph, and indeed our collaborations predate the PIRE by about a decade. We've had various collaborations with various sources of funding, and our interest then has been in comparing these materials that have both silicon carbon and silicon oxygen bonds with materials that do not. And we're continuing the work right now with work on a number of fibers. This, I think, is something that I believe we will have as a poster, and also some work now on some nano materials with Gabriela. So our contribution to PIRE then is complementary indeed to the theoretical calculations. What I always tease Peter about is that when we disagree, it makes for interesting discussions. And when we agree, there's always the possibility that we're both wrong. So it's exciting to do this sort of science in the interdisciplinary group we have in PIRE. The next slide, please. A little bit less than 3 years ago, I moved from University of California, Davis to Arizona State University. It was a return because, in fact, I had started my career at ASU back somewhere in the Precambrian. Stayed there for about 16 years, went to Princeton for 12 years, and then spent more than 20 years at UC Davis. And I decided, after having been friends with people at ASU and having some conversations, that there was a real opportunity to build new programs here, to rebuild solid state sciences, which had been very, very active in the 1970s and 1980s, and to rebuild it in the context of interaction with a very strong program in planetary sciences. And what I have called the new program that we have is the Center for Materials of the Universe. So Materials of the Universe intentionally includes everything, but it basically includes two concepts that we are pursuing. If I may have the next slide, please, Silas. And that is that the excitement we have now in planetary science, both in the exploration of our solar system, with manned, unmanned, perhaps indeed landings, etc., and of course the thousands of, and now I think it's over 5,000 exoplanets that have been discovered. It liberates us from thinking just about the evolution of one planet, our Earth. It liberates us in terms of composition, temperature, pressure, and time. And it poses what I call the biggest inverse problem in material science. Namely, a forward problem is, here is a material, what are its properties? An inverse problem in the planetary context is, here are a few observations on an exoplanet hundreds of light years away. Its position from its sun, the nature of the sun, its size, maybe a little bit of spectral characterization. For those of you who are students, the arsenal of things we will learn about planets will increase during your careers. But still, it's an inverse problem that says, what are the properties of the planet? What is the planet? What is its chemistry? What is its structure? What is its evolution? Based on really incomplete evidence. And there, of course, we need evidence from the constraints of cosmology, geophysics, geochemistry, and especially material science. So MotU, the Center for Materials of the Universe, explores these issues with a number of faculty, students, etc. And the second issue that we explore is, of course, in order to get more information about planets, in order to make space exploration, either robotic or even with humans, more amenable, more survivable, more interesting, one needs better materials. So one needs more radiation resistant materials, one needs lighter materials, one needs to be able to make materials in space. If one sets up bases, let's say on the moon, one cannot bring everything, one is going to have to make materials from local resources. All of these are, in a sense, classic materials problems. In another sense, totally non-classic, because the conditions of low gravity, variable temperature, variable atmospheres, etc., are of course very different from what we know on Earth. So MotU seeks then to basically, and I will ignore that, MotU seeks then to bring people together to work on that. And basically, next slide. Our accomplishment so far is that we have some new faculty hired. Hongwoo Shu, who's come from Los Alamos National Laboratory, and Jie Shu, they're not related, who's come from University of Texas, El Paso. Hongwoo works on thermodynamics, structures, hydrothermal work, etc. Jie works on transition metals and their role in both chemical and geobiological processes, and we're very glad to have them. We're in the process of hiring more faculty. We were essentially promised 5 faculty positions, of which so far we have filled 2. And of course, we have students and postdocs working on issues related to MotU. We have a website, we have a lot of collaborations, we are planning workshops, etc. We're writing grants, proposals, etc. Some we succeed at, some we don't succeed at. And the next thing that I want to talk about and really concentrate on is one grant proposal that we have indeed succeeded with, because this offers opportunities for all sorts of research, including research on polymer-derived ceramics and other materials. And this is something that we call FORCE. The next slide, please. The Facility for Open Research in a Compressed Environment. A little bit of a force on the name, but never mind. And it is going to be a national center at ASU, funded by an implementation grant from the National Science Foundation. This was an all NSF competition, although our home part of NSF for this is Earth Sciences. In fact, this was a situation where we had to compete NSF-wide, and we basically have succeeded. Kurt Leinenweber is the principal investigator. He was a graduate student of mine at Princeton who fell in love with high pressure some 30 years ago, and he came to ASU to run a high pressure facility long before I came back. Myself, David Smith, who's an electron microscopist, Tom Sharp, who's a geologist, geochemist, planetary scientist, Dan Shim, who does diamond cell research, are the co-PIs, and we have a very large group of interested people, potential users for the facility. So what are we going to be doing? The next slide shows a little bit of the history, because you don't get something like this started out of thin air. And in fact, this is something we could not have done at Davis because it simply does not have the history and the people. So very briefly, in the 1970s, 1980s, when ASU was growing perhaps even more rapidly than it is now, it is still growing fairly rapidly, we built solid state science, partly with an emphasis on electron microscopy, also with an emphasis on geochemistry with John Holloway and myself. We established our first calorimetry lab here. And then I left in 1985 to go to Princeton, and Paul McMillan, who unfortunately died 8 months ago, was a graduate student of ours who then joined the faculty at ASU and eventually left for University College London. And he started a high pressure effort funded by an NSF MRSEC for a few years to develop high pressure research. We built a high pressure lab, including then some multi-anvil apparatus. And we gradually then did establish ourselves in the high pressure game. And then 3 years ago, just when I came here to ASU, there was an opportunity to put in a big proposal to NSF. And there had been a decadal review of NSF Earth Sciences, which suggested that very large multi-anvil presses, such as exist in, well, you could guess, Germany, Japan, and now China, but not in the United States, are something that one should do in the context of high pressure research, planetary research, Earth research, etc. So having that written in a report probably helped get the grant. But what really helped get the grant was getting the community solidly behind us, identifying a large group of interested people who hopefully will become users. And the grant was funded starting October 1st of last year. So this is very exciting, and we're spending a lot of time in developing high pressure research. The next slide reminds you that what one can do at high pressure is generally make samples at pressures into the megabar range. The amount of sample you can make, the size of the sample you can press, is to some extent inversely proportional to the pressure you want. And if you're in diamond cell research, your pressures are almost unlimited. They go into the megabar range, but your sample sizes are in the microgram range. We have a separate project right now that I will refer to a little bit toward the end in thinking about what sort of thermodynamics we can do on microgram size samples. But in general, one needs to make larger samples, both for in situ measurements, some of which are at synchrotrons, some of which are not, and for measurement of physical properties, transport properties, elastic properties, etc., so that if one can make samples in the milligrams or better hundreds of milligram range at different pressures and temperatures, one can have materials for studies. If one makes the samples here, one can study them here, but one can also study them elsewhere. People can make samples and take them home for whatever measurements they want. So what are we getting in the high pressure center? What is force buying? Next slide, please. So basically, the equipment that we have now all ordered then, and this was decided upon with a lot of discussion with the community, both before the grant was funded and after the grant was funded, we will be getting 4 major pieces of equipment. The pièce de résistance is a 5,000 or 6,000 ton uniaxial split sphere apparatus, a so-called multi-anvil, which we've christened Ichiban, and which we are getting from Sumitomo in Japan, and which Japanese research groups have a lot of experience with. Its comfort range for operation is up to about 25 GPa. and its temperature ranges up to about 2000 degrees C, depending on what sort of sample assemblies and heaters. These are typically resistance heaters that you put into the apparatus. And the samples that can be made range from being several hundred milligrams in the lower pressure range to a few milligrams in the highest pressure range. The second instrument we're getting, and they had a lot of discussion about it and a little bit of change, is a so-called 1,000-ton dia press. Excuse me a second. Hello? I cannot talk with you now. So a dia press that can go up to not quite the megabar range, but perhaps the 0.8 of a megabar range. Larger samples at lower pressure, smaller samples at higher pressure. And this is going to be the exploratory press for really very high pressure research. We're going to get a torsional press, which we're calling twister, basically, which will enable the study up to a few tens of GPa at temperatures up to a few hundred degrees C, with the hope of extending the temperature range to really look at the effect of twisting, the effect of torsion on high pressure materials, on their physical, making them their physical properties, phase transformations. And finally, we're getting a gas vessel, which operates at lower pressure, of course, but with very large samples. And this will be used in part for geochemical studies of systems with fluids, but also for the initial synthesis of large amounts of material that can then be taken to other laboratories or for other studies. We will complement this, of course, with supporting equipment. We will complement it with all the different facilities available at ASU. And where we are in the process of making this happen, the first 2 years are planned then for deciding and ordering the equipment. The delivery times on the equipment are typically on the order of 18 months. So we're looking for something like the fall of 2023 for the equipment to be ready. We are also looking for the renovations for the laboratory, which is going to be housed in a building very near the chemistry building where my labs are and Kurt's initial high pressure lab is. And we're very much in the detailed planning process, having chosen contractors, etc. So all of this is going along reasonably on schedule, with, of course, all of the ifs, buts, and maybes of the current political and economic situation. But so far, so good on both the equipment and the renovations. The next slide. So we will be a national facility. This is not just something for ASU users, although, of course, we have a large group of users. We hope to be a focal group for high pressure research in both material science and earth and planetary science, with visitors coming to use the equipment, with then a setup where the visitors can have a desk, conference rooms, etc., with interactions in terms of workshops, town meetings, etc. And of course, the long-term goal, since this implementation grant is for 5 years, is to somewhere around year 4 begin to have users, begin to have projects, and about year 5 to begin to transition into normal operations. Normal operations need money, so I anticipate that we will be writing a lot of grant proposals. I'm optimistic enough to think that NSF did not put $13 million into a facility in order to, and then stop funding its operation. But obviously we have to write good proposals, be successful, keep the community behind us, and look for funding above and beyond the National Science Foundation. We estimate that running the laboratory properly will take about $1 million a year. So this is an ambitious project. We have the backing of ASU. ASU is funding part of the construction that isn't directly with the equipment. And so far, so good, again, in the way that everything is going. The next slide.
That's your last slide.
My last slide. Okay.
Yeah.
So then let me talk about basically some of the things that FORCE can do that might be of interest in terms of our current projects, in terms of MotU, and of course, in terms of PIRE. One of the things we do not know in any detail is how polymer-derived ceramics and fibers and so on respond to pressure. We know that for normal silica, one has phase transitions in the solid state, the quartz to coesite to stishovite, and stishovite is the rutile structure, so we get octahedral silicon in that structure. We know that silica glass can be densified at pressure. We know that if we take something like stishovite, the octahedral form, and decompress it, and then heat it, it transforms to a glass which appears to have properties slightly different from that of normal silica glass, which then on heating to higher temperature, perhaps reverts back to normal silica glass. We can ask similar questions for phases in the silicon-carbon-oxygen system. We can ask similar questions for things containing nitrogen and boron as well. One of the unanswered questions in polymer-derived ceramics, and one of the things that makes them scientifically interesting, is in general, if one makes amorphous materials, one imagines that there is an underlying set of crystalline materials with similar bonding but long-range order. So far, in the systems that we've been studying, the silicon, carbon, oxygen, nitrogen, even boron system, those kinds of crystalline phases really have not been discovered. The question is, do they exist? Do they exist perhaps as pressure, either a catalyst or a contributor for the phase stability of some new materials in these phases? Can one order the nanostructures in some way to decrease the volume and therefore have them made at pressure? So I think that FORCE will open a number of avenues for research. I want to end by talking about something I alluded to at the beginning, and that is getting back to very small samples. Very small samples mean samples, on the microgram size or tenths of a microgram. Why are those interesting? First of all, in diamond anvil cell experiments, of course, that's the kind of samples you make. Secondly, in multi-anvil experiments or even one-atmosphere experiments, you often make multi-phase materials. You make materials that have a few interesting grains in them that you would like to study further, that you would like to separate from your main matrix, but that again are available very typically as micron-sized grains. What sort of calorimetric measurements, what sort of thermodynamics can you do on them? We have a Mettler-Toledo fast scanning calorimeter, which is essentially a calorimeter on a chip, that enables heating rates up to thousands of degrees a minute. But the important thing is that it is effectively a DSC for microgram and sub-microgram size samples. We have to make this quantitative rather than simply a tool for observation and kinetic studies. One needs to do two things: calibrate the sensors and then deal with how one measures the mass of a sample, which is actually too small to be measured accurately on a microbalance. We have done this basically and are going to publish something very shortly. And we believe that using this calorimeter together with diamond cells, together with samples that are small for other reasons, will open a whole field of study, some of which again can be applied to the projects in PIRE. So PIRE chooses a set of subjects. MotU expands those subjects to the universe, and we've been thinking quite a lot about whether silicon, carbon, oxygen phases might exist in the interior of the Earth or in planetary interiors. And FORCE greatly expands the capabilities one has for studying these materials. Thank you.